Okay, so hello everyone. Today I'm going to show some feature from DeepSeek as well as Gemini. As you know that we are moving towards explanatory reasoning. So I'm trying to rate the existing large language models, especially Gemini and DeepSeek, with respect to solving problems that needs only to be solved in a few lines. That means we don't have to over-explain or overcomplicate the solution. So here my midterm. So it's a part of the parallel and distributed computing. So this is the problem. A pipeline processor has a clock rate of 1.5 gigahertz and executes a program with 2 million instructions. The pipeline has 6 stages, and instructions are used at a rate of 1 per clock cycle. Ignore penalties due to the branch instruction and out of sequence execution. Compute the speed up of this processor for this program compared to a non-pipeline processor. Of course, so the first thing that we don't have to use all this data. So that means that we don't have to compute CPI, we don't have to compute the time needed to execute 2 million instructions using pipeline and non-pipeline stages. So instead, we could go for the relative. That means so we go back into the formula. So the formula to compute the speed up using k pipeline stages is S subscript k, which is equal n times k, divided by k plus n minus 1. N is the number of instructions, and k is the number of pipeline stages. In our case, k is equal 6, and n is equal 2 million. As you can see that n is larger compared to k, which means that the denominator k plus n minus 1 can be approximated by n minus 1, and n minus 1 can also be approximated by n. So in total, the speed up will be approximately k. So here, that means that for this particular example, the speed up will be equal to 6. That means the pipeline version of the processor will be 6 times faster than the non-pipeline stages. This is very simple questions and also very simple answer. Now let's see how DeepSeek try to answer this. So here is the DeepSeek. So I gave it the same problem. So you can see it's up here. Solve the following problems. I gave the problem, and you can see that it took 148 seconds to compute this. And he want all these calculations, so he computed the number of instructions times CPI, and he tried to reason, and then he did the loss of computation. Okay, you see how complicated is it? Okay, so he plunged into very complicated calculations, and then he used the formula speed up, which is equal time without pipelining, time or divided by time with pipelining. And then he went on to computing, so the time without and with pipelining. And here made some clarification, and here he computed everything. At the end, he found that this is almost 6, okay? And again, he came on to reasoning, the same stuff. And at the end, he provided the same solution. You see that? Okay, so this is the speed up. So he computed the, for non-pipeline processor, this is the summary, the total cycle number of instruction times CPI. I don't know, it's not really needed to use the CPI formula here. The clock rate, and then the time for the non-pipeline. And for the pipeline processor, the time, okay, he computed this one. And then he computed the speed up, which is almost equal to 6, which means that the conclusion that the speed up of the pipeline processor compared to the non-pipeline processor is 6. You see, it's very, I mean, for me as a professor, if the student will give me all this calculation, I will get lost following the reasoning. And this is what we call overcomplication, so the complication, which is, I mean, normal with the with large language model. Now let's see how Gemini will react. So I'll go now live with Gemini. Okay. Good morning, good afternoon, Gemini.